Hello everyone, and welcome to this webinar on the development of domestic engineering technologies. So the agenda for this webinar will cover the heating timeline, typical domestic heating technologies, grid electricity, and modern solutions, followed by a short quiz to test your understanding of the presentation. First, let's look at the heating timeline. Heating all started with the discovery of fire over 1.9 million years ago. It is then believed that fires moved indoors for heating between 7,500 to 5,700 BC. A major breakthrough in the timeline of heating was the concept of central heating, which is where one central heat source is able to heat an entire building. This concept is first believed to have been developed in ancient North Korea and was later developed by the Romans. As we can see here, the buildings were raised on plinths to allow for warm air from a fire to circulate under the building, heating the whole floor as a result. After the fall of the Roman Empire, very little development was made in heating. Central heating was practically forgotten and people returned to fires for heating. In the year 1200, the chimney was invented, which now enabled smoke to be removed from properties, as well as in improving the output of fires through a constant airflow known as the stack effect, which is continuously driven by buoyancy. Next came the invention of the stove approximately 200 years later, which improved the controllability of wood burning and allowed for heating to internal rooms away from the chimney. Coal was discovered in the West in 1679, which offered a cheaper alternative to wood as a source of fuel. At the time, global warming was unknown, and therefore the severe consequences of burning coal was sadly not understood. The first water-based central heating system was installed in 1710 using an adjacent river. Central heating then developed further by the invention of a domestic steam boiler in 1790 that circulated hot steam around pipework. Next came the development of the gas-fired stove in 1802 for both heating and cooking. This invention paved the way for gas to be used as the primary heating fuel, with over 80% of UK homes today run on gas. In 1805, ducted warm air central heating was invented, which drew on the earlier concept of underfloor warm air heating. The addition of the ducts and floor grills allowed for warm air to be delivered directly into habitable spaces of a property, as opposed to the previous concept of having the warm air underneath the floor heating the entire floor, making this strategy more efficient. Warm air heating is still found today in some homes, most typically in the Midlands. The first thermostat was invented in 1830, which allowed for central heating systems to be automatically turned on and off to regulate temperatures. The radiator was invented in 1855, which is arguably one of the most important inventions in the history of heating. The radiator allowed for efficient heat transfer from water central heating pipework, which was not previously available, paving the way for the rapid growth in water-based central heating. Most of us today will have radiators in our homes. The heat pump was first invented in 1856. A heat pump is a device that can heat a building by transferring thermal energy from an outside source, such as air, water, or the ground, using a refrigeration cycle as shown. Some models of heat pumps can also be utilized for cooling our buildings by reversing the heating operation of the refrigeration cycle. The first direct electric heater was developed in 1883 using closely packed bulbs, which gave off heat as a byproduct of electrical resistance. Piped water underfloor heating was invented in 1905, offering an alternative and sometimes more effective solution than the radiator due to its ability to heat large surface areas at lower temperatures. So this is our simplified domestic heating timeline, meaning the majority of the systems typically found in homes today were actually first invented over 100 years ago. These have obviously been significantly developed and have become much more efficient over time. So let's take a deeper look into central heating, and then we'll look at some of the domestic heating technologies available today. This graphic demonstrates the historic slow growth of the heating industry, the majority of UK homes not having a central heating system almost 7,000 years after the concept of central heating was developed. Until 1970, central heating was regarded as something only for the upper classes and was too expensive for typical households, with most still relying on a single fireplace as a source of heat. With developments in manufacturing resulting in falling costs, central heating quickly became the norm, with 95% of homes run from central heating systems today. The main issue with the sudden rapid growth in central heating was that almost all installed systems were designed to operate by burning fossil fuels, such as gas and oil, which were much cheaper to run than electric solutions. So these are the most common heating solutions installed in the UK today, and almost all of you are likely to have one of these heating systems installed within your home. So firstly, we have the open fire, which is around 30% efficient. We then have a wood burner, 60 to 80% efficient. Warm air heating, 80 to 85% efficient. Gas stove, around 85% efficient. Boiler, 85 to 100% efficient, depending on the fuel source. Electric radiator, 100%. Air source heat pump, 200 to 400%. And ground source heat pump, 300 to 500% efficient. As you can see, the heating efficiency, i.e. the useful conversion of energy input to heat output, varies significantly for the different systems, with heat pumps being by far the most energy efficient method of heating currently on the market. To understand air source heat pumps, we first need to understand the relationship between air temperature and the efficiency of the system. As can be seen by the graphic on the left of the screen, the warmer the air temperature, the more efficient the heat pump is at converting electricity into heat. Please note that the efficiency values will vary between different heat pump models and manufacturers. This concept also explains why ground source heat pumps are even more efficient than air source heat pumps, as the temperature of the ground is fairly constant year round and is much higher than that of air during the peak winter heating period. So even though the concept of the heat pump was invented in 1856, development was slow due to the higher costs of electricity and significant investment into fossil fuel boilers dominating the market. It's important to note that during this time, even though the concept of global warming was not fully realised, the vast majority of electricity was generated by coal, which is considered as significantly more polluting than both oil and gas. Therefore, at the time, heat pumps were not the solution to combating global warming, even with their superior efficiencies. To reach the carbon target set out by the UK government, almost 100 times the number of domestic heat pumps installed in the last 170 years will be required to be installed within a 12-year period. This means 600,000 heat pumps will need to be installed per year until 2035, which involves huge investment and upskilling of the industry. So, why the current drive towards heat pumps and electricity? To understand why, we need to take a look at grid electricity. Historic grid electricity was generated by burning coal and other fossil fuels such as gas and oil, emitting high levels of CO2 into the atmosphere. And the electricity grid today is made up of a number of sustainable and renewable sources, such as nuclear, hydropower, solar, and wind, alongside the existing fossil fuels, resulting in reduced carbon intensity for the grid. This diagram shows the typical split of fuel source for the UK electricity grid. We can see that natural gas still holds the greatest share in the grid, but is now only slightly higher than renewables, which will soon overtake. The phasing out of coal and oil has accelerated over the last 50 years, with 88% of UK electricity generated by these two fuel sources alone in 1971. They now account for less than 5%, and coal will be phased out completely in 2024. The carbon conversion factors for the primary fuels in the UK grid are displayed to the right of the screen, which provide the amount of carbon emitted per unit of energy delivered. The combination of fuels used today results in a grid carbon factor of around 0.19 kilograms of CO2 per kilowatt hour, which is set to be reduced to around 0 kilograms of CO2 per kilowatt hour by 2035 through the introduction of more renewables and nuclear energy. So, what are the modern solutions today powering our homes alongside heat pumps, which we've already discussed? The following video provides an insight into home solutions available today.
Nature elegantly converts the sun's energy from one form to another. These energy transformations happen around us every day in our cities, homes, and cars. But unlike in nature, we need to convert solar power with an inverter. These inverters turn solar energy into home electricity, convert power into hot water, cool and heat up our homes and buildings with HVAC systems, store solar energy in a battery to use in the evening, and even charge our electric cars. Inverters are turning our homes and businesses into smart energy ecosystems. One smart inverter can manage all of the home's energy needs. But inverters do more than just managing our home's energy. They convert and manage energy in our electric vehicles, office buildings, factories, data centers, and more. Since these inverters are all around us, they can work together in a network to smartly manage energy. They transform our PV systems, batteries, and other appliances into energy resources for the grid, turning each of us into active energy participants and producers. This will revolutionize the grid into a decentralized energy network and power our world based on a new clean energy economy. By improving the way we use and consume energy, Solar Edge is powering a better future for us all.
So that video demonstrated how solar panels can be used towards powering our homes with clean renewable energy, and we'll expand on that in the next couple of slides. This graphic displays a typical operation of a domestic solar panel installation with battery storage on a peak summer day in the UK. The green curve demonstrates the amount of solar energy generated. The red curve shows electricity purchased from the grid. The darker blue curve shows the direct solar energy consumed, and the transparent blue curve shows the consumed electricity from the battery storage system, whilst the orange curve shows solar electricity exported back to the grid. The spikes in the morning and evening for the electricity consumption reflect typical morning and evening activities, such as putting the kettle on or cooking. So Here we can see that around 5:30 a.m. the solar electricity generated is greater than the electrical demand. So at this point, all electricity consumed is now from the solar, which is both free and renewable. Here, electricity is sold back to the grid at 15 pence per kilowatt hour, as enough solar electricity has been generated to fill the battery, whilst also meeting the electricity demand. At around 5:30 in the evening, the solar generation falls below the electrical demand for the first time, and therefore the battery kicks in to provide the evening electricity. Without the battery, the household will now have to start paying for their electricity from the grid. If no charge remains in the battery from the day before, then the electricity can be purchased overnight at off-peak rates, typically between 12 a.m. and 7:30 a.m. During winter, when solar generation is typically less than the electrical demand for a property, the battery will not be charged. However, the battery can be filled up from cheap off-peak electricity overnight and then discharged during the day during peak periods to save costs. Electricity generated from solar becomes even more beneficial when coupled with a heat pump, as the free and clean electricity generated by the panels can be converted into up to 5 times that for heating or hot water. We can further increase our energy efficiency of hot water via smart hot water cylinders, such as the Mixergy cylinder shown. Compared to a conventional tank, this cylinder is capable of heating our hot water up to 5 times faster. It can deliver up to 30% more hot water, allowing for a smaller tank to be installed, and it can provide a reduction in energy of typically between 20 to 40%, saving both carbon and cost. So, how does it work? The cylinder shown on the left is a traditional hot water cylinder. Cold water is fed into the base of the cylinder, which is then heated via heat exchange between an indirect coil filled with hot water from a heat source such as a boiler, or via a direct electric immersion heater. The hot water tank is controlled via basic time controls, which simply turn the heat source on or off to heat the whole tank of water. The cylinder on the right is the smart hot water cylinder, which has the same heating elements as the conventional cylinder. However, they are located at the top of the cylinder. Rather than pumping cold water into the bottom of the tank, the cold water is pumped to the top of the cylinder and is sprayed in via a nozzle to allow for diffusion. The spray nozzle and top-down heating approach allows for us to choose exactly how much water we would like heated within our tank. The amount of hot water can either be controlled via an app or can be calculated from machine learning to develop an optimized weekly schedule based on our personalized hot water usage. The effect of the smart cylinder approach to heating the hot water cylinder is demonstrated by the top row of the graphic shown on screen. In the image, we can clearly see the thermal stratification occurring, which allows for the control of how much hot water we would like to heat, whilst providing us with more hot water in a shorter space of time. The bottom graphic for the conventional cylinder shows how adding the cold water in at the base of the cylinder results in dilution of the hot water, taking longer for the tank to heat up whilst consuming more energy. These smart hot water cylinders can also work as thermal stores, taking excess electricity from the grid and storing them in our cylinders for free, creating a similar decentralized heat network to the battery solution we saw before. So that was just a brief overview of a small number of the innovative products available. If you're interested in finding out more on modern solutions to home energy, then check out the Fully Charged show on YouTube and watch any of the videos in the Clean Energy playlist. Equally, if you're interested in solar panels and battery storage, the Solar Edge YouTube channel has some great tutorials and demonstrations. So that was an overview of the development of engineering technologies, and hopefully you can see that what was historically a slow-growing industry has taken off over the last 50 years and is growing at an exponential rate, making now a very exciting time to be within the building services industry. Now we have a few multiple choice quiz questions to test your knowledge of what we learned in this presentation. So, question 1. What was the first source of central heating? Was it A, fireplace, B, stove, C, underfloor water, or D, underfloor air? Question 2. What is the most efficient technology for heating? Is it A, boiler, B, electric radiator, C, heat pump, or D, wood burner? Question 3. What is the typical efficiency of an air source heat pump? Is it A, 80%, B, 200 to 400%, C, 100%, or D, 300 to 500%? Question 4. Why is a ground source heat pump typically more efficient than an air source? Is it A, ground temperatures are higher than air during winter? Is it B, ground source heat pumps are bigger? C, ground source heat pumps are manufactured better? Or D, all of the above? Question 5. How does air source heat pump efficiency vary with increasing air temperature? Is it A, decreases, B, increases, C, does not change, or D, not sure? Question 6. How many heat pumps does the UK plan to install by 2035? Is it A, 2 million, B, 6 million, C, 14 million, or D, 8 million? Question 7. What is the current majority source of electricity in the UK grid? Is it A, natural gas, B, renewables, C, nuclear, or D, coal? Question 8. How do we plan on reaching a UK grid carbon factor of around 0 kilograms of CO2 per kilowatt hour by 2035? Is it A, solar, B, wind, C, nuclear, or D, all of the above? Question 9. What can we do with excess solar energy that we generate? A, store it in a battery. B, use it to heat hot water. C, export it to the grid. Or D, all of the above? And finally, question 10. Why are smart hot water cylinders more efficient than conventional models? Is it A, they utilize machine learning? B, they spray in cold water to allow for diffusion? C, they heat from the top down to heat only what we need? Or D, all of the above? Okay, so now we'll have the answers. So firstly, question 1 is D, underfloor air. Question 2, C, heat pump. Question 3, B, 200 to 400%. Question 4, A, ground temperatures are higher than air during winter. Question 5, B, increases. Question 6, D, 8 million. Question 7, A, natural gas. Question 8, D, all of the above. Question 9, D, all of the above. And finally, question 10, also D, all of the above. Thank you very much for listening. I hope you've enjoyed the presentation.